Good evening, Bearcats. I am so excited that you're in my class, and I'm so excited that you'll be flipping with me this year, and we are going to get our first lesson started. Okay, this is section 1.1 on our pre-cal, of course, and I want to make sure that you're labeling your spiral notebooks really carefully because I will be checking those for a grade, but more importantly because they will be invaluable to you when you go off to take your next class in your calculus class, whether that be at Klein here or at your college next year. So let's get started. This is 1.1, like I said, rectangular coordinates. We're going to talk first a little bit about the Pythagorean theorem and maybe just take a little bit of a twist on the way you look at the Pythagorean theorem. It's very familiar to you. It comes from geometry. We're going to make that tie in to our distance formula, which is mainly an algebra skill, because pre-calculus going into calculus is, of course, this great marriage between algebra and geometry. So we're going to take a look here first at our Pythagorean theorem is a squared plus b squared equals c squared, something you're very familiar with. Just want to talk a little bit about what a is. A is really that distance or that length of that line segment. And that's a vertical distance, so this would be your y value and this would be your subsequent y value. And so that length would be found by a change in y, which would be y2 minus y1. And you're going to notice that tie-in a minute when I write the distance formula. You can also think of it as delta y, change in y. All right, and that's much more pre-cal and calculus talk. All right, next thing we're going to do is our x value or our b value would be horizontal change. And our horizontal change, remember Pythagorean theorem is only true for right triangles, so our x value change, this would be our x and our x, and so we would have x sub 2 minus x sub 1 would be the change in our x sub 2 minus x sub 1, change in our x value, which would be our b value in this case, or our delta x, which is the change in x. So when we look at the distance formula, and this is familiar to you, you're going to see a little bit more of it here in a minute, but you're going to have x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. And notice the y sub 2's come from here, the delta x or the change in the x comes from here, and they tie back into our Pythagorean theorem. So I just want you to start right off the bat in pre-cal making these great connections between geometry and algebra. The next thing I want you to look at is we're going to set up in your notes every day, at least for the first chapter, you will have, and maybe all year, but for the first chapter for sure, we've decided we're going to set up 3-column notes. 3-column notes. We're going to outline those for you, so it shouldn't be a hard thing, but it's a really great way to keep some things organized. So I'm going to bring up the next slide, and when I do, you're going to want to pause, and you're going to want to write down your columns in your notes. It is also something I will be checking for tomorrow for a grade. So go ahead and get ready, and I'm going to pull up that worksheet. All right, here we go. So this is what your 3-column notes should look like. So you're going to want to pause and you're going to want to write down what we have here. So after you pause, go ahead and work out your distance problem and your midpoint problem. Those are the ones for you to work out. So where it says work out, I'm going to look tomorrow to see if you actually work those problems out. But you do want to set it up in those 3 columns. After that, you're going to want to go down and you're going to want to copy down the first 2 columns in your notes. Tomorrow when you come to class, you're going to go to your textbook and you're going to find where those formulas are and you're going to write them in, and then you're going to sketch those shapes. Sketch those shapes. I'll give you a little hint. Oops, I don't think it's going to let me write on here. Doesn't let me write on here. I'm going to give you a little hint. The hint is page 7. I believe you'll find that information on page 7 of your textbook. So while you're working on your worksheet tomorrow in class, I'm going to come by and check your notes for these 3-column notes. So make sure you have them down. It will be a grade. All right, the next section for tonight will be 6 problems we're going to work together. You have 18 problems to complete in class tomorrow. These are 6 of those 18 problems. There are also 6 problems that should help jog some of your memory skills from Algebra 2 and help you be more successful on the rest of that worksheet tomorrow. It will be due at the end of the class. It will be graded for accuracy, so please make sure and take this seriously. If you have these 6 problems in your notes, then tomorrow you can just write, circle that problem and write in notes, and then I will know not to penalize you for that. So we'll have done those together. If you have not for some reason, then you'll want to go ahead and work them. All right, so the first one we're going to see here is a compound inequality. I like to use number lines in solving my inequality, and I want to talk a little bit about the difference between an and an or statement. This is an and statement, and typically in our and statements, it means that the information must be true for both the left side of the equation, or the equation on the left, and the equation on the right. So the solution set must be true for both equations. So visually on a number line, that's where those values would overlap, because that would make them true for both. So we're going to look at it in both ways. So the next thing we're going to do is go ahead and solve these two inequalities. On the left, I'm going to go ahead and subtract my 3, and of course I would get negative 3x is less than 9, and then I'm going to divide by a negative. Oh, please, please, please don't forget, when you divide by a negative in an inequality, you must reverse your sign. So when I divide, I will get x is greater than negative 3. That will be this solution. On the other side, of course, I'll add the 16, and I'd have negative 5x is less than 30. And then I would divide by a negative again, so I'm going to reverse my sign, and I would get x is greater than negative 6. All right, so those are my two solutions. Let's look at these on a number line and see where they overlap, because that would be true for both. All right, we have a negative 6 over here. We have a negative 3 over here. Also notice that there is no equality. It's just greater or less than, no greater and equal to part. So at these particular values, we will have an open circle, notice signifying that they're not inclusive. So they don't include those points. They are just either on either side. This says x is greater than negative 3, so that's going to go in this direction. This says x is greater than negative 6. It's going to go in this direction. So we have to be really careful here. The values from negative 3 that are greater than negative 3 would be true for both equations. The values between negative 6 and negative 3 are only true for one of the equations, so it is not true for both. And because this is an and, you have to choose negative 3. So your solution would be from negative 3 to positive infinity. We're going to write an interval notation. Because we have an open circle, it's not inclusive. We will have a soft bracket, meaning it's not inclusive. And of course, infinity always gets a soft bracket. There is your first problem. Way to go, Bearcats. All right, pause and write down what you need, and then I'll be right here waiting for you. Okie dokie, here's our next one. We have an or statement. It is another compound inequality, but an or statement. An or means that it could be true for one of your equations or the other, not necessarily true for both. It could be true for both, but it does not have to be. Typically, your graphs, number line looks like this, not always, but number line looks like this, because it would be one direction or the other. Let's take a look and see if we have any unusual circumstances here. When I solve the left side, I would subtract the 3, and of course I'm going to get x is less than negative 2. When I do the other side, I'm going to subtract the 5, and I'm going to get negative x is less than 7, and then of course divide by a negative 1, and that means I have to reverse my sign, and I will get x is greater than negative 7. So those are my two solution points. Now, let's take a look again on a number line. So we have a negative 7 at this end. We have a negative 2 down here. Once again, no equality, so not inclusive, open circles. Let's read what this says. It says x is less than negative 2, so this is going to go off in this direction. This says x is greater than negative 7. This is going to go off in this direction. Oh, we have a little bit of an issue here. It doesn't look exactly like our little traditional or picture. So let's think about this. It can be true for one equation or the other, which means it also could be true for both. So all of these solutions in the middle would be true for both. The solutions that continue on this side would be true for the second equation, or the one on the right. The solutions on this side would be true for everything less than 2, which would be the first equation. So it could be true for this or this. So that means it looks like everything is covered, and in this case it's a special situation where you could say that it's all real numbers, or preferably interval notation, which would be negative to positive infinity. All right, let's keep going, Bearcats. Pause if you need to write down. Okie dokie. Next one is number 8 off your worksheet for tomorrow. This we're going to deal with quadratics. Notice I have already written down the problem and the old traditional quadratic formula. There are, the first line of defense in quadratics, in my opinion, would be to factor. That would be the easiest path. But if it's not factorable, then you would want to use your quadratic formula. We also have completing the square as another method, so you can also do that if that's what you remember. I'm going to take a look here, and to solve most of our quadratics, we're going to want to set them equal to 0. Also remember, in solving our quadratics, what are we really finding? We're finding the, hopefully you answered, x-intercepts, which are also called our roots and our zeros. So there are multiple names for those same points. All right, so let's take a look and go 3x squared plus 5x plus 7 equals 0. I'm going to take a quick glance at whether I can factor this or not. And this is what I do. I take my first number, my last number, I multiply together. I think 21. 3 times 7 is 21. And then I think, can I have factors to multiply to 21? Can I have numbers that multiply to 21 that would give me 5, whether I added or subtracted? And the only multiples of 21 I can come up with besides 1 and 21, which won't give me 5, would be 3 and 7, which would also not give me a combination of 5. So I don't believe I can factor. So I'm going to go straight to quadratic formula. Well, my 3 would be my A value, my 5 would be my B value, and of course my 7, my constant, would be my C value. So I go ahead and make note of that, and then I'm going to ask that you always show your substitution into the quadratic formula. So this would be negative B, so it would be negative 5. Plus or minus the square root of b squared. Well, since b is 5, 5 squared is 25. I'm going to go ahead and square it right before I put it in there. Minus 4 times a is 3, c is 7, all over 2a, which would be 2 times 3. The next thing I'm going to do is I'm going to reduce this a little bit, make it simpler. Notice I don't have a calculator. I'm going to have negative 5 plus or minus the square root of some number, all over 2 times 3, which is 6. Well, once I figure out that sum number, I believe this time we'll come up with a negative 59. And I noticed something interesting. I have a negative under a square root. We know that that's a bit of a no-no, and that is an imaginary term. So we're going to have an imaginary number, and because of that, we have a complex imaginary number. We're going to go ahead and extract that negative and substitute it with an I. And I know you probably remember all of this from Algebra 2. So I would have negative 5 plus or minus the square root of 59I over 6. Now, I would be fine just leaving it just like this as your answer. If you would like to put it in the proper A plus bi form, then you would write it as negative 5, 6 plus or minus the square root of 59 sixths I, and there's your proper form. So either one of these I would take. All right, make sure you write that down, and we'll keep going. We got 3 more to go. All right, next we're going to start with some exponential equations, solving some exponential equations, properties of exponents. Properties of exponents. Hopefully, I may have a handout for you. If I don't, then we'll go back and review those, but hopefully you remember your properties of exponents. We're going to solve this. Since the variable is on the left, it's a little difficult to raise that to a power, so we want to move that to that exponent to the right side. So we're going to clear it out on the left. And one of the properties of our exponents, if you raise a power to a power, you multiply. So I can take this entire thing and raise it to a power. I'm going to raise it to its reciprocal, because when I raise it to its reciprocal and I multiply, it'll become 1. And anything to the first power is itself. So I basically clear that out. I also have to go on the other side and also raise it to that same power. So when I do, these kind of cancel each other out and become 1. Therefore, I'm left with just 2x minus 5 equals 27 to the 2/3 power. All right, so let's take a look at this. We know that the bottom of that fraction in an exponent is the root if we want to change it to radical form. So that would become the cube root of 27, and the top becomes the exponent raised to the, or the power to the second power, and that's how we're going to write that. You could put the 2 inside with the 27. That becomes a really large number that I don't want to have to think through since I don't have a calculator. All right, so let's go on. So we have 2x minus 5 equals, the third root of 27 would be 3. So now we have 3 squared, which would be 9. And now we just finish up our math. We're going to add the 5, so we have 2x equals 14. And of course we divide and we get x equals 7. Go Bearcats. Make sure you're always looking in case there's any issues with exponentials or exponents. You probably don't have many problems with extraneous solutions, but we will see that coming up next. Pause, and I will see you in a minute. All right, we got a couple of situations, a couple of different things here. We have a radical, which means that we need to watch for our restrictions because we just talked about that we can't have a negative under a square root. We also have an inequality, so that means we could have a range of solutions. So we've got a couple things going on. The very first thing I see if I have fractions or I have square roots or even roots is I watch for my restrictions. I'm really careful about watching for my restrictions. So the first thing we're going to do is take a look at the restriction. All right, the first thing I know is that x plus 3, that value under there cannot be negative. It could be 0, but it cannot be negative. So it has to be greater than or equal to 0. If I move the 3, that means my x value itself would have to be greater than or equal to negative 3. So that's really important. That's going to be important in our solution set in a minute. So I always figure that out first. Then I go ahead and solve the problem and find out my other end of my other solution or restriction. So I'm going to take my square root and I'm going to actually square it, and that will clear out my square root. I'm going to have to also square my 4. So that will cancel out my square root. I will get x plus 3 is less than or equal to, what did I do? That should be just a square. 4 squared is 16. Then I'm going to subtract the 16, or subtract the 3, and I will get x is less than or equal to 13. That's my other point of my restriction here on my solution set. So let's take a look again on a number line. I'm a big number line person. I have a negative 3 down here. I have a 13 up here. Something different that we didn't see before is that I have an equality here. So these will be solid because they will include, they'll be inclusive, they'll include those 2 points. This says x is greater than negative 3. This said x is less than 13. So it appears to me that all the solutions in between here will be the correct answer. So our answer will be from negative 3 to 13 inclusive, so we get hard brackets in our interval notation. Just a little reminder, when you get to radicals or square root graphs have a stopping and then they move on to the right in its parent graph form. So that's why there's a restriction. It can't be on the left. Now, if they've been reflected or something in a graph, you will see it a little differently, but that's the basic parent graph, and that's just kind of visually gives you that restriction set. In this case, it's between it's probably a line with like number 4, and so it's between here and here, okay? And maybe this has been moved over because it got shifted over, so maybe your graph looks like this, and it's between here, and this is the solution set. And I hope that didn't confuse you. If it did, we'll talk about it in class tomorrow. All right, we got one more to go, and you are done. All right, our last thing tonight is to talk about logarithms. Logarithms are huge in calculus. It's a big thing, part of your math going forward, and we're just talking about some simple properties that we're trying to refresh our memory on. I hope you remember your log properties. If you don't, we can look those up, or maybe I'll have a little handout for you. But again, one of the things that you have to remember is to solve for a log. There's several things. One, often you must condense them so that you only have one log on either side of your equation you're trying to solve. The other thing is often you will have to change forms from logarithmic to exponential to actually solve them, or vice versa. Let's take a look at this one. I don't think we have to change anything here, but this will demonstrate our one-to-one property. They all are log base 3, so they all share a common base. This side, it's almost like you're combining like terms, so to speak, but you have to condense that log to be able to solve it, so there's only one on either side of the equation. So when I do that, since they share base 3, I can write it as 1 log base 3. Because it's subtraction, I'm going to take the 2 and the x and I'm going to condense it together with division. If it were addition, I would condense it with multiplication. So it's going to be 2 over x equals log base 3, 4. Now, this is a one-to-one property. These are the same bases. These are the same log bases, so they are already equal to each other. So we really don't need to worry about that too much. We're just going to solve 2 over x equals 4 over, and we'll put it over 1. So we're going to solve 2 over x equals 4 over 1 to find our x value. I like to cross multiply to keep down any mistakes. So of course I have 4x, 4 times x is 4x, equals 2 times 1 is 2, divide by 4, and x is 1/2. Often if you go too quick in this little step, this is a very good place to make a careless mistake, and you'll tell me it equals 2, which is not true. All right, so x is 1/2. And as long as when we plug the 1/2 back into our logarithm and it doesn't create a 0, because we can't have the log of 0, then we're in good shape, or a negative. All right, so I think that's it for tonight. I hope you have a good evening. I will see you tomorrow. Be ready to work hard so that you get a good grade on that first paper. I'm glad you're in my class. Welcome to success. Night, Bearcats.